Here is something that should bother you. You have used electricity your entire life. You flip a switch every single day, and the explanation you were given, the one that seemed perfectly reasonable, the one that clicked together like a neat little puzzle, that explanation is wrong, not slightly off, not missing a footnote, wrong in a way that goes all the way down to the foundation. The energy that lights your bulb does not travel through the wire. It never did. I am not being clever. I am not setting up a rhetorical trick. I want you to sit with that sentence for a moment before we go any further. Every lamp, every motor, every appliance you have ever touched in your life, the energy powering those things did not come through the wire. And by the time we are finished here, you will see exactly what I mean, and you will not be able to look at a wire the same way again. Let me start by giving the standard picture its fair hearing, because it really is a lovely picture, and the people who built it were not fools. You connect a battery to a bulb with two wires. The bulb glows. What happened? The battery creates a voltage, a kind of pressure difference. That pressure shoves electrons along the copper. They flow out of one terminal, through the wire, through the filament, back through the other wire, back into the battery. A complete loop. The electrons carry energy from the source to the load. The filament resists their flow, gets hot, glows. Done. You can teach this to a 12-year-old. Current is the flow of electrons. Voltage is the push. Resistance is the opposition. Multiply current by voltage and you get power. Everything locks together beautifully. And for designing circuits, calculating fuses, choosing wire gauges, this picture works perfectly well. Engineers use it every day. Bridges do not fall. Machines keep running. So why am I telling you it is wrong? Because something is hiding inside that picture. Something nobody mentions in the first explanation. And once you pull it out and look at it, the whole thing unravels. Here's a very simple question. How fast do the electrons actually move through the wire? Most people, if you ask them, will say something like, well, electricity travels at nearly the speed of light, so the electrons must be flying. That seems reasonable. You flip a switch and the light comes on instantly. So those electrons must be moving extraordinarily fast. Let us do the arithmetic. I love arithmetic. Nature cannot lie to you through arithmetic. Take a typical household copper wire, 2 millimeters in diameter, carrying 10 amperes, the kind of current a toaster draws. Copper has roughly 85 billion free electrons per cubic meter. Each copper atom donates about 1 electron that wanders freely through the metal. The wire is absolutely packed with mobile charge. Now 10 amperes means 10 coulombs of charge passing any given point every second. Each electron carries about 1.6 times 10 to the minus 19 coulombs. Work out how fast the electrons need to drift on average to produce that current through that wire. The answer is about 0.02 of a centimeter per second. That is roughly 1 inch every 2 minutes. A garden snail moves about 50 times faster. If an electron started its journey from the power station and tried to drift its way to your house 1 mile away, it would take that electron approximately 400 years, 4 centuries. The electron would have set off during the reign of Queen Elizabeth I and still would not have arrived. And here is the part that makes it even stranger. Inside the copper, those same electrons are already moving at roughly 1 million meters per second, bouncing violently off copper atoms in every random direction like pinballs gone haywire. That thermal velocity is enormous, but it is random, equally in every direction, so it produces zero net movement anywhere. The drift I just calculated, that tiny crawl, is a minuscule bias layered on top of all that frantic chaos. Imagine a crowded train station with thousands of people rushing in every direction, going nowhere on average. Now a gentle breeze pushes everyone just slightly toward the exit. That lean is the drift. The frantic rushing is the thermal motion. The lean is about 10 billion times smaller than the rushing. And yet, because there are so astronomically many electrons all leaning together, that collective drift adds up to 10 amperes of current, enough to run your toaster. So, the electrons are barely crawling, less than an inch per minute, and yet the light comes on the instant you flip the switch. Those two facts cannot both be true if the electrons are the things delivering the energy. Something else must be carrying it. And that something travels at nearly the speed of light while the electrons creep along at glacier speed. That is your first clue that the standard picture is hiding something important. Now, the usual response to this puzzle is actually clever, and I want to give it credit. People say, sure, Individual electrons move slowly, but the signal propagates fast because the wire is already full of electrons. Push one in at this end, one pops out the other end almost immediately, like a tube packed with marbles. Push a marble in one end, and a different marble exits the other end right away. The pulse travels fast, even though each individual marble barely moves. This is a decent analogy up to a point. The electrical signal, the disturbance, does propagate through the wire at roughly 2/3 the speed of light. There is a rapid chain reaction of nudging, one electron pushing the next, and in a tiny fraction of a second, the disturbance has traveled the length of the wire. But think carefully about what that analogy is actually saying. In the marble tube, when you push one marble, the kinetic energy hops from marble to marble through the material of the tube. Each one physically transfers energy to the next. Is that really what happens in a wire? Is energy hopping from electron to electron through the copper? And if so, there is a second puzzle that is even worse. Energy in a circuit flows in one direction, from the battery to the bulb, but electrons fill the entire loop. They are everywhere. How does the energy know which way to go? Why does it flow from battery to bulb and not the other way? The marble analogy breaks down here. Something more subtle is happening. And the real answer, when you finally dig it out, is startling. The energy is not in the wire at all. Let me approach this from a completely different direction. Forget electrons for a moment, forget wires. Let me talk about fields. In the 1860s, working in Scotland, James Clerk Maxwell did something I rank among the greatest intellectual achievements in human history. I mean that seriously. Before Maxwell, electricity and magnetism were two separate subjects with some curious connections between them. Ørsted had shown in 1820 that a current deflects a compass needle. Faraday showed in 1831 that a changing magnetic field induces a current, but nobody had a unified picture. Nobody had asked, what are the deep rules governing how these two phenomena interact? Maxwell took the relationships discovered by Coulomb, Ampere, Faraday, and others, and welded them into a single coherent framework. 4 equations. That is all. 4 equations describing how charges create electric fields, how there are no isolated magnetic poles, how a changing magnetic field produces an electric field, and how a moving charge or a changing electric field produces a magnetic field. Then Maxwell did something audacious. He noticed his equations implied something nobody had asked for: waves. An oscillating electric field creates a magnetic field. That magnetic field, as it changes, creates an electric field. The two leapfrog each other forward through empty space, carrying energy as they go, needing no material medium whatsoever. Maxwell calculated the speed of these waves using only the known electrical constants and got 300 million meters per second. He recognized that number immediately. It was the speed of light, measured by entirely different means. The coincidence was too perfect. Maxwell concluded that light itself is an electromagnetic wave, visible light, the radiation from the sun, the stuff our eyes detect, oscillating electric and magnetic fields propagating through space. That realization, published around 1865, unified optics with electromagnetism in a single stroke. And it had an uncomfortable implication for circuits. When current flows through a wire, there is an electric field along the wire driving the electrons forward, and there is a magnetic field circling around the wire because moving charges generate magnetic fields. Ampere told us that. So around every current-carrying wire, you have both an electric field and a magnetic field existing in the space outside the metal. And Maxwell has just told you that electromagnetic fields carry energy. So are those fields around the wire carrying energy? How much? In what direction? In 1884, a physicist named John Henry Poynting sat down and worked out the answer. Poynting was methodical, careful, not flashy, and what he found turned the standard picture completely upside down. Poynting derived a formula. Take the electric field at any point in space. Take the magnetic field at the same point. Compute their cross product. The result is a vector, a quantity with both magnitude and direction. The magnitude tells you how much energy is flowing through that point per unit area per second. The direction tells you which way the energy is heading. This became known as the Poynting vector. People enjoy the coincidence. It points, literally. Poynting applied his formula to the simplest possible situation: a straight wire carrying a steady current. What he found was, to put it gently, disturbing. Near the surface of the wire, the electric field has 2 components. One runs along the wire, the field driving the electrons forward, produced by the voltage drop. The other points radially outward from the wire, produced by tiny amounts of charge that accumulate on the surface of the wire to maintain the proper voltage gradient along the circuit. These surface charges are rarely mentioned in introductory courses, but they are there, and they are essential. Meanwhile, the magnetic field circles around the wire in closed loops, as Ampere's law demands, so you have a radial electric field, an axial electric field, and a circumferential magnetic field. When Poynting computed the cross product at the wire's surface, the result pointed inward, radially inward, from the surrounding space into the wire. Let me make absolutely certain you catch what that means. The Poynting vector at the surface of a current-carrying wire points from the space outside the wire into the wire. The energy is not flowing along the wire. The energy is flowing from the surrounding space into the wire, perpendicular to it, from all around it. At a light bulb filament, the Poynting vector plunges inward from every direction, energy pouring from the surrounding electromagnetic field into the resistive material, where it is converted into heat and light. The wire is not a pipe transporting energy. The space around the wire is transporting energy. The wire is more like a drain, pulling energy inward from the field surrounding it. I know the expression on your face right now. I have seen it many times. You are thinking this cannot possibly be right. Hold on to that feeling. It is honest, and it is exactly the reaction the physics has to fight against. Oliver Heaviside, working independently in England at roughly the same time, reached the identical conclusion. Heaviside was a remarkable figure, self-taught, reclusive, cantankerous, and brilliant. He took Maxwell's original formulation, which sprawled across roughly 20 separate equations, and compressed it into the 4 clean vector equations we use today. He essentially invented vector calculus as a practical tool for physics, and he was blunt about what the Poynting vector meant. Heaviside said flatly that the idea of energy traveling through the wire is wrong. The energy travels in the electromagnetic field. The wire is a guide, not a carrier. And Heaviside had practical motivation for caring about this. The great technological problem of the late 19th century was the undersea telegraph cable. Thousands of miles of copper on the floor of the Atlantic, carrying signals between Europe and America. The cables were a nightmare. A sharp dot sent from London arrived in New York as a slow, smeared blob. Lord Kelvin analyzed the problem using the wire as pipe model. Useful work, but limited. Heaviside looked at the same problem through the lens of fields. He realized the signal was not really traveling through the copper. It was traveling in the electromagnetic field, in the insulating layer between the central conductor and the surrounding sea. The geometry and the electrical properties of that insulating gap determined how the signal propagated. Heaviside developed the mathematical theory of transmission lines, still used by every electrical engineer today. And that theory is fundamentally about fields, not about electrons marching through metal. The irony is that the establishment rejected his work for years. The Royal Society refused to publish some of his papers. He died in poverty. But he was right. Every time you use a coaxial cable, every time a signal travels through a transmission line, you are depending on the physics Heaviside understood. Let me offer an analogy that helps clarify things. Think about a river flowing through a canyon. The canyon walls do not carry the water. The water flows through the open space between the walls. The walls shape the flow, constrain it, make it useful. But nobody looks at a river and says the rock walls are transporting the water. The water moves through the gap the walls create. A wire is like the canyon walls. The electromagnetic field is the river. The wire shapes and guides and organizes the field. But the energy lives in the field, in the space around the wire, not locked inside the metal. This is a complete inversion of the way most people think about circuits. Consider what a battery actually does in this picture. A battery does not inject energy into the wire the way a pump forces water into a hose. A battery maintains a charge separation, positive on one side, negative on the other, through chemical reactions that push charges against the electric force. This separation creates an electric field. That field does not exist only inside the wire. It spreads outward through the surrounding space, shaped and guided by the surface charges on the wire. The battery establishes the field carries the energy. And those surface charges deserve more attention because they are the unsung heroes of the whole arrangement. When a circuit reaches steady state, tiny amounts of charge sit on the surface of the wire, not uniformly, but in a gradient from one end to the other. This gradient is precisely what maintains the electric field inside the wire that drives the current forward. But those same surface charges also produce a field in the space outside the wire. That external field, combined with the magnetic field from the current, is what the pointing vector operates on. The surface charges are the mechanism by which the wire structures the surrounding field. Without them, the field outside the wire would be formless, and energy could not flow in any organized way from source to load. It is a remarkably intricate self-organizing system. The battery sets up the initial field. The field redistributes surface charges. The surface charges reshape the field. The reshaped field carries energy from source to load, all of it happening in a fraction of a second when you close the switch. The electrons inside the wire drift slowly, responding to the electric field. Their motion sustains the magnetic field. The combination of the two fields determines where the energy goes. The electrons are not porters carrying luggage from the battery to the bulb. They are more like the canyon walls, maintaining the geometry of the field through which the energy actually flows. Now you will ask, if the wire is not carrying the energy, why do we need the wire at all? Why not just remove it and let the field do its job? Excellent question. And the answer reveals the partnership between field and matter. Without the wire, there is no closed circuit. Without a closed circuit, there is no sustained current. Without current, there is no steady magnetic field. Without the magnetic field, the pointing vector drops to zero. No energy flows. The wire provides the path for electrons. The electrons provide the current. The current provides the magnetic field. The magnetic field combined with the electric field produces energy flow through the surrounding space. Remove the wire and the entire pattern collapses, like removing the canyon walls and watching the river spread into a useless thin sheet over flat ground. The channel directs the flow, but the channel does not carry the flow. That distinction matters. Let me push this further with a thought experiment that has quietly unsettled physicists for over a century. Imagine a circuit. A battery on one side, a light bulb 1 meter away. Instead of short wires, you connect them with two wires that each stretch 300,000 kilometers outward, loop around, and return. Roughly the distance light travels in 1 second. Total wire length about 600,000 kilometers. Close the switch. How long before the bulb begins to glow? If energy traveled through the wire following the copper, it would need to traverse 600,000 kilometers at roughly 2/3 the speed of light. That takes about 3 seconds. But that is not what actually happens. The moment you close the switch, the electromagnetic field begins to reorganize. That reorganization propagates outward from the switch at the speed of light in every direction. The bulb is 1 meter away. In about 3/billionths of a second, the field change reaches the filament. The pointing vector at the filament surface becomes non-zero. The bulb begins to faintly glow, almost immediately. Not at full brightness. Full brightness requires steady current throughout the entire circuit, and the electromagnetic signal still needs those 3 seconds to travel down the long wires and back. So what you would observe is a dim initial glow, brightening gradually over the following seconds as the circuit settles into steady state. The first energy arrives through the field, cutting directly across the 1 meter gap. It does not wait for electrons to start circulating around the enormous loop. The field gets there first, because the field is what carries the energy. Where does that initial energy come from? It was already there, stored in the electric field that surrounds the battery even before the switch was closed. When the switch closes, the field reconfigures and some of that stored energy propagates to the bulb. Nothing from nothing. The energy was already in the field, waiting. Now let me show you something that borders on the absurd, and I think you should see it, because it reveals just how real these fields are. Imagine a stationary electric charge sitting in space. Next to it, a stationary permanent magnet. Nothing is moving, no current flowing, no work being done, just two objects sitting quietly. Compute the pointing vector. Cross the electric field with the magnetic field at every point in the surrounding space. What you get is a vector that circulates, energy flowing in closed loops around the two objects endlessly, with no beginning and no end. Nothing is moving, nothing is being generated or consumed, and yet the formula says energy is flowing in circles through empty space around two things just sitting there. Students look at me like I have lost my mind when I show them this, and I understand why. Energy going in circles forever for no apparent reason. What kind of physics predicts that? Here's the part that should genuinely disturb you, that circulating energy carries angular momentum. Real, physical, measurable angular momentum. If you try to separate the charge from the magnet, you have to account for that momentum. It shows up in experiments. It has been measured. It is real. The pointing vector is not a mathematical bookkeeping trick. It is telling you something true about the physical world. Fields contain energy. Fields contain momentum. They are physical things, not diagrams on a blackboard. Physical things that push, pull, carry, and flow. In my own teaching, I tell students, look, I know this sounds obviously nuts. Our theory says electrons get their energy not from being pushed along the wire, but from an electromagnetic field pouring in from the surrounding space. Intuition screams that energy should flow along the wire, but the mathematics says energy flows in from the sides. And I call it obviously nuts, because the first time you hear it, that is exactly what it sounds like. Then you do the calculation. Compute the total energy flowing into the surface of a resistor using the pointing vector. You get current squared times resistance, exactly Ohm's law. Compute the energy flowing out of a battery. You get exactly the power the battery ought to deliver. Watt for watt. No fudge factors, no adjustments. The agreement is perfect, and it has been perfect for over a century. That is when you stop arguing with the equations and start retraining your intuition. Now, why does this matter beyond the classroom? Consider alternating current, the kind from your wall outlet. In AC, electrons do not even drift in one direction. They oscillate back and forth 60 times per second, moving less than 1/100th of a millimeter. They go nowhere. They vibrate in place. And yet energy flows steadily from the power station to your house. If electrons carry the energy, this is completely mysterious. Particles that go nowhere delivering energy from somewhere else. But if energy lives in the field, it makes perfect sense. The oscillating current creates an oscillating electromagnetic field. That field propagates energy outward from the source through the space around the wires to the load. The electrons shake. The field carries. The electrons sustain the field pattern, but they are not the messengers. Take a radio antenna. Oscillating current runs up and down it. Oscillating electric and magnetic fields build up around it. Those fields propagate outward through empty space as a radio wave, carrying energy miles away to a receiving antenna, where the oscillating field pushes electrons back and forth, recreating the original signal. Energy traveled through space in the field with no wire connecting the two endpoints. If you already understand that even in a simple battery and bulb circuit the energy travels in the field outside the wire, then radio is just the natural next step. The training wheels come off. The field goes out on its own. A coaxial cable is a beautiful illustration. Inner conductor, outer cylindrical shield. The electromagnetic field is contained entirely in the gap between them, that annular region of what looks like empty space. All the energy flows there. Compute the pointing vector inside a coaxial cable, and energy flows parallel to the cable axis through the gap, not through the metal. That is why coaxial cables work so well for carrying signals. They are engineered to contain and guide the field precisely. The outer shield keeps the field from leaking out. The inner conductor and the geometry of the gap shape how the field propagates. The metal defines the boundary conditions. The gap does the work. Let me balance this before I finish, because some people swing too far the other direction when they first hear this. They say, right, so the wire does not matter. The field is everything. Throw the wire away. That is just as mistaken as the original picture. The wire is essential. Without the wire, there is no closed path for electrons. Without electrons flowing, there is no current. Without current, there is no magnetic field. Without the magnetic field, the pointing vector vanishes. The electrons are slow, yes, but they are the keepers of the field geometry. They are not energy carriers. They are channel maintainers. Compare a superconductor to a normal wire. In a superconductor, electrons flow with zero resistance, no energy lost. The pointing vector at the surface of a superconductor runs parallel to the surface, not inward. No energy is absorbed by the wire. Perfect guidance. In a normal resistive wire, the pointing vector tilts slightly inward. Some energy from the surrounding field enters the metal and becomes heat. More resistance means more tilting, more energy absorbed. In a light bulb filament with high resistance, the pointing vector plunges nearly straight inward from all directions. Energy pours in from the surrounding field, is absorbed by the resistive tungsten, and emerges as heat and light. The energy does not arrive through the ends of the filament like water through a hose. It arrives from outside, converging inward from the field surrounding the wire on all sides. Field carries the energy. Matter shapes the field. Neither works without the other. The field without the wire diffuses uselessly. The wire without the field is dead metal. Together, something marvelous emerges, and nature shows no preference between fields and particles. It uses both, each enabling the other. Let me pull everything together. The standard model says electrons flow through wires and carry energy from source to load like water through a pipe. This model yields correct numerical answers for currents, voltages, and powers. It is a useful tool, and it is not going anywhere. But it misrepresents where the energy actually lives and how it actually moves. The correct picture, the one that falls directly out of Maxwell's equations and Poynting's formula, says that energy is carried by the electromagnetic field in the space surrounding the wire. The field flows from the source outward through space, guided by the wire, and enters the load from the outside. The electrons inside the wire play an indispensable role in maintaining the field configuration, but they are not the energy carriers. The field is. This is not interpretation, it is not philosophy, it is what the equations demand, and every experiment conducted since 1884 is consistent with it. Why care about the deeper picture if the simpler one gives correct answers? 3 reasons. First, because the deeper picture is the true one, and there is value in understanding how nature actually operates, even when a convenient simplification suffices for everyday calculations. Knowing the truth opens doors that the simplified picture keeps closed. Second, because the field picture is essential for understanding anything beyond simple DC circuits. Radiation, antennas, waveguides, electromagnetic interference, wireless transmission. If you learned from the start that energy lives in wires, making the leap to fields feels like a foreign language. If you understand from the beginning that even a boring battery and bulb circuit has its energy in the surrounding field, everything else follows naturally. Third, because it is beautiful. The realization that the seemingly empty space around an ordinary wire is actually teeming with flowing energy, that is a glimpse behind the curtain at how nature really operates. It makes the world feel larger and stranger and more wonderful than it did before, and it connects to something deeper still. Newton's gravity acted instantaneously across empty space with nothing in between. That always troubled people. It troubled Newton himself. He called it an absurdity, though it worked, so people used it. Maxwell changed that. With electromagnetism, the field is the mediator. A charge here does not reach across and directly push a charge over there. The charge here creates a field. The field fills space. The distant charge responds to the field in its own immediate neighborhood. Everything is local. The field is the messenger, the carrier, the medium, and it is as real as the charges that generate it. When you think about the Poynting vector wrapping around a wire, you are touching that idea with your fingertips. The space around the wire is not nothing. It has energy. It has momentum. It has direction. It is doing something specific, measurable, and essential. It is as full and as active as the wire itself. More so, in fact, because that is where the energy actually lives. So here is the image I want you to carry. The next time you flip a light switch, think about what is actually happening. The circuit closes. Surface charges redistribute almost instantly along the wire. The electric field and magnetic field configure themselves in the surrounding space. Energy flows inward from that surrounding field, converging from every direction into the filament, where it is converted to heat and light. The room brightens. The light in your room is not powered by electrons trudging through copper at a snail's pace. It is powered by invisible fields filling the space around you, carrying energy at nearly the speed of light from distant generators through the air you are breathing, converging on the glowing filament. Those fields are present right now. Every wire in this building, every cable, every cord is surrounded by an electromagnetic field carrying energy through the space you occupy. You cannot see it, you cannot feel it, but it is is as real as the floor beneath you, and it is the thing actually doing the work. The wire is not the story. The wire was never the story. The field is the story. That seemingly empty, apparently unremarkable space surrounding a simple piece of copper. That is where all the action is. That is where the power flows. And the wire, for all its solid copper weight, is just the guide, standing at the edge, pointing the way. If someone had told me years ago that the most important part of any electrical circuit is the empty space around it, I would have thought they were joking. But nature has a sense of humor like that. The most important things are very often the ones you cannot see. So the next time you notice an ordinary wire plugged into a wall, think about what you are not seeing. The fields wrapping around it, the energy streaming through invisible space, the entire electrical universe humming quietly in the air around that simple piece of copper. That is the real electricity, and it was there all along, right in front of you, waiting for someone to notice. Here is my question for you. If you could somehow make the electromagnetic field visible, if it glowed in proportion to the energy flowing through it, what do you think a simple lamp plugged into the wall would actually look like?